Hello, everyone, and welcome to the bi-monthly Intermountain West Regional Drought Early Warning System webinar with the National Integrated Drought Information System, or NIDIS. I'm Gretel Fallingstad, the Intermountain West Drought Early Warning System Coordinator. And we begin this briefing by respectfully acknowledging that the land we are joining from today is the ancestral land of Indigenous peoples. As we are in different parts of the country, this will be different for each of us. But the land from where I'm joining is the traditional lands of the Tewa people or Santa Fe, New Mexico. These drought webinars include announcements from NIDIS in addition to the current drought conditions and outlooks for coming weeks. And announcements today include a solicitation for nominations of a drought expert by the national academies. This QR code will send you to the link that you see on this slide to nominate an expert. Nominations are due by January 24th, 2025, and we would greatly appreciate you spreading the word for that nomination. Currently, across the Intermountain West, drought exists in all of the 5 states, primarily in Arizona, with 56.4% of the state in drought and 11.2% of that at D3 or above. Colorado sits at 10.4% and just above or almost to 1% at D3 or above. New Mexico is at 29.1% in drought, 5.2 D3 and above. Utah, 18.9% of the state is in drought, 0% of that is D3. Wyoming is suffering the worst impacts of drought at the moment, with 96.3% of the state in drought, with 22.4% of that being D3 or above. I want to take a moment to introduce our speakers and make another announcement about our snow drought update, which Dan McAvoy will share more about in his presentation. But these snow drought updates are a series for winter 2025, and the first snow drought update will be available on NIDIS's website, which you can find with this link on the right side of the screen, or go to that QR code tomorrow. Our speakers today include John Mayer from the Utah Climate Center. He is the Assistant State Climatologist at Utah Climate Center. He specializes in research to operations to address Utah's climate services, as well as operational numerical weather and climate modeling. John has enjoyed pursuing topics focused on understanding Western U.S. hydroclimate and precipitation changes in both the winter snowpack and summer monsoon seasons. In addition to his research to operations work, John Mayer also serves on the Utah Drought Task Force and is the state coordinator for the CoCo-RaS network. Next, we will hear from Dr. Dan McAvoy. He is a researcher with the Western Regional Climate Center and Desert Research Institute. His research is interdisciplinary and spans the fields of climate hydrology and meteorology. His research interests include advancing drought monitoring technologies, seasonal drought prediction, climate variability, and the role of evaporative demand on drought, quality and uncertainties in assessments of weather observations, and climate modeling. So without further ado, I will hand off the presentation to you.
Thanks, Gretel. Let's go ahead and get my screen share.
Let's see.
All right, how are we looking on that?
Perfect.
Great. Well, we'll go ahead and start with the Intermountain West Drought Status Update. My name is John. I'm from the Utah Climate Center, and I appreciate the opportunity to speak with everybody. We'll begin our journey here with a recap of the temperatures over the recent months and seasons. On the left is our November temperature percentiles for the region. The blue colors that dominate most of the Intermountain West represent below normal temperatures for the November month. Areas in whites are in the near normal, and then a very few areas in Wyoming and New Mexico with those yellow grades and orange grades are warmer than normal in the top 33 or top 10 percentiles. So November overall for the region settled into below normal conditions, which is quite opposite to what the September, October, November fall months and season looked, which we can see on the right. Very opposite color grades for the season as a whole. Our temperature percentiles for just about everywhere in the Intermountain West represents well above normal conditions, region-wide, just about everywhere experiencing the top 10 percentile, and you can see those darkish red-orange colors there, sort of sprinkled across the region are record warmest conditions. So overall, a very warm fall season that ended with a cooler stretch in the month of November. From a precipitation point of view, the same figures here, November precipitation percentile on the left, and we see the central portion of the Intermountain West in Utah, Colorado, and then down into New Mexico experienced above average precipitation for the month of November, whereas Arizona and Wyoming, where we have the greatest drought impacts currently situated, experienced below normal precipitation. Now, the fall months in general for this region is quite dry from a seasonal and annual perspective. So we take these with a little bit of a grain of salt for percentiles. However, we do look at trends over the season. And when we look back across the September, October, November period, the region-wide trend overall is towards drier conditions. Arizona and Wyoming experiencing the greatest deviations from normal. A great deal of the far southwestern portions of the southwestern U.S. Experiencing record driest conditions with very little to no precipitation. A lot of the Utah, Colorado, New Mexico portion of that fall season is really dominated by a couple of more impactful events towards the end of November around the Thanksgiving travel time. So really across the season as a whole, very dry with just one or two impactful events that flip the script for a large deal of those positive anomalies. Overall, hot and dry. The collection of that hot and generally dry fall season drove the drought expansion across much of the Intermountain West. We can see this 3-month change map in the class changes across the region. Yellows and oranges representing increasing drought impacts or drought degradation, and areas of green representing improvement in drought classification. And we can see Wyoming and Arizona, where we had the hotter and drier conditions, experiencing the highest magnitude of drought degradation. The areas of eastern Colorado and New Mexico, where they had a fairly good amount of precipitation delivered, seeing drought improvements. So depending on where you're at, drought changes have been one side of the coin or the other. But overall, the Intermountain West as a whole has seen some fairly substantial drought degradation in areas that are already experiencing drought conditions. Current snowpack across the region, and I won't step too much on Dan's toes, knowing that he's going to give a really nice presentation on snow drought. This is an overview of where we currently stand according to the NRCS's SNOWTEL, which are high altitude snow observing systems across the high terrain in the region. The color scale here is intuitive, and you can see relative to this time of year, areas that are reds and oranges and yellows are below normal, blues and greens are above normal. And again, really the only areas that are positive for this time of year are found in central Utah and throughout Colorado, a little bit of northern New Mexico as well. Overall, the region as a whole, we could probably consider as underperformed for this time of year for snowpack content. When we look at year-over-year trends, which is always a nice thing to consider for snowpack accumulations, the figure on the right shows the collection of all those SNOWTEL observation stations with their year-over-year changes. Stations featuring red colors are drier than this time last year, with blue are wetter than this time last year. And again, The general pattern here is we see the benefit of a couple of big impact storms that moved through central Utah and Colorado that really jumped up the snowpack for those regions. The rest of the Intermountain West has suffered from, I would guess, a general lack of consistency of snow accumulation for this time of year. So we're behind schedule a little bit. Soil moisture is something that we keep a very close eye on as we head through the late fall months into the early winter months, because that translates to spring runoff efficiency when it comes time to melt our snowpack. And what we see across the region is, again, sort of a developing situation of soil moisture deficits in areas that have experienced the hotter and drier fall months. And that should translate and carry over to a less efficient spring runoff come March and April when we're melting that snowpack down. Again, the same very similar pattern in Utah, Colorado, and New Mexico, where a couple of beneficial late fall storms really drove up that topsoil soil moisture, and we're going to be banking on those areas, holding on to that through the freeze season, and hopefully translating to a more positive spring runoff efficiency come that time of year. Year-over-year trends are shown on the right, and again are helpful to give us an understanding of how things might translate from snowpack to spring runoff to reservoir recharge. And we see year-over-year trends very much echoing what we've seen in past figures here, where Wyoming, Arizona, parts of northern Utah, and a few areas in New Mexico have seen year-over-year reduction in soil moisture content. And we look at the snow-tail sites themselves, and again see very similar patterns regionally of where we have areas of concern marked by red and areas of a little bit more optimism marked in blue. So where you find areas of red in these maps here are areas where we are certainly concerned about what will be going on in terms of the snowpack season, and watching for that, and positive trends from the snowpack side of things. From a soil moisture point of view, those areas of red are points of view where reduction in efficiency is likely to sponge up any of the melt that occurs early on in the spring, and won't translate as much to spring runoff and reservoir recharge, as that water just kind of hangs around in the landscape and doesn't run off into the river systems. Now, there's a lot of ways that we could slice the drought pie, and for lack of extended time of just talking about this stuff, these multi-drought indicators are really helpful in condensing a lot of things into a single graphic that nicely visualizes areas that are experiencing short-term drought pressure or drought relief, and long-term drought pressure and relief. The figure on the left is the short-term conditions, looking over the recent few weeks to months, and looking at how conditions have affected the landscape. Very much the perimeter of the Intermountain West has experienced short-term drought pressure and long-term drought pressure when you switch over to the figure on the right. Areas east of the Rockies in Colorado and New Mexico, those really nice beneficial storms that have moved through this fall, kept things cooler and wetter, have presented nice drought relief, both on the shorter term timescales, very obvious there, and on the longer term timescales as well. The Four Corners area region as a whole has sort of held steady, and that's an area that has experienced more long-term pressure in the past. So it's nice to see a lack of drought pressure being applied into that area for a change. All right, we'll move on to looking forward in time now that we've done a recap here. Look at the drought outlook. La Niña update is something that we've been watching since the summer. The expectation of the development of a weak La Niña has been in the forecast discussions for about half a year now. As we stand right now, entering the early week of December here, ENSO neutral conditions still remain present in the Pacific. So we have not emerged that weak La Niña that was predicted to occur. It's still just barely hanging on right under the threshold for an official La Niña classification. So it's kind of just flirting with us right now on the development of that official declaration. However, the expectation is that will continue to just barely creep through that threshold over the coming months, and persist through the January through March window of time with that weak La Niña conditions. Based on that expectation, the 3-month outlook by the Climate Prediction Center remains very much mirrored with the historical expectation for a La Nina type of winter, and that is warmer and drier conditions straddling the southern latitudes of the United States, the Southwest being an area that experiences nice statistical relationship with that. As you transition to the northern portions of the Intermountain West, you go through that saddle point where we have equal chances for a normal type of winter. This is December, January, and February outlook. And then maybe the highlight of our outlook is that portions of northwestern Wyoming is sitting in favorability for above average precipitation. That's the area that's experiencing maybe the greater drought impacts as we stand right now. So it would be wonderful to see this materialize and to see those storm systems deliver a nice winter season to Wyoming specifically. The rest of the region, however, is looking a little bit more bearish in terms of our outlook for precipitation. Temperatures being warmer than normal this time of year isn't a huge impact in terms of loss of soil moisture and everything. So we'll hope to see a majority of our winter precipitation fall and hold on to that as snowpack into the spring months. The weather pattern expectations behind this 3-month outlook is driven very much by a very persistent weather pattern that I've indicated here with a graphic that the meteorologists will like to see, but maybe a few other people are familiar with. What we're looking at here is an ensemble predictability of the average weather pattern in the middle atmosphere. And those red colors represent favorability for high pressure, blue colors represent favorability for low pressure over the next 3 months. And the type of weather pattern that we see here, again, very much reflects the type of La Nina pattern that we would expect, even though we're still straddling that very weak La Nina neutral conditions right now. But the take-home message that we're seeing right now in the extended range forecast models is that this type of weather pattern introduces the types of winter storm systems that are pretty wimpy. They're very moisture starved. They don't have a lot of Pacific moisture. There's not a lot of atmospheric river events moving through the region. We kind of jokingly call these nickel and dime storm events. And so while this pattern doesn't necessarily block everything from moving through the region, and we don't have any accumulation, we don't have a very overwhelming type of high impact snowpack events that really drop multiple feet of snow over and over again that are just really moisture laden. So while it looks like this type of weather pattern will allow storm systems to move through, they probably aren't as substantial as we would like to see for an ideal type of weather pattern for drought relief. I guess the one caveat here is this type of weather pattern will benefit the Wyoming portion of the Intermountain West, which is where we have the greatest drought impacts. And so we'll be crossing our fingers that that materializes. Seasonal drought outlook from the Climate Prediction Center remains bearish for most of the region. The map on the left with all those browns and yellows represent either drought persisting in the brown or drought development likely in the yellow colors. The northwestern portion of Wyoming is the only area in the Intermountain West where drought removal or drought improvement is expected. So depending on where you're at, mostly bad news for the Intermountain West in terms of the winter outlook. Favoring a little bit of better news for Wyoming areas, at least in portions of the northwestern states there. Obviously, the central and northeastern part of Wyoming is where we have the greatest impacts of current drought, with D3 accumulating there. So, yeah, overall, a lack of precipitation and the types of storm systems are not presenting a great deal of optimism for the seasonal outlook from a drought perspective. To summarize everything, although November ended cooler region-wide and wetter in the central portions of the region, the fall season was quite a bit hotter and mostly drier than normal across the Intermountain West. And that has not set the stage very well heading into the snow accumulation season. So far right now, our snowpack is generally behind schedule across the region. The exception there is central Utah and Colorado, where we had a couple of high impact events blast through at the end of November. The context here is the early season start to snowpack doesn't have a great correlation with the end of season results. And you could think about this year might be more of a tortoise versus the hare type of analogy, where our year might look more like what the tortoise is doing, where we just kind of slowly plod our way through and hopefully end up ahead of the faster race that we might have with bigger impact events. The reduction of soil moisture across the region year over year and the status that we're in right now sort of pulls back our optimism for the spring runoff efficiency next spring. However, their reservoir levels across the region are very high right now after a couple of years of really good snowpack and spring runoffs. So we do have somewhat of a viable safety net for short-term water deficits entering next year, should this year play out like it has begun. Seasonal outlook favors drier and warmer southwestern U.S. winters, equal chances for normal winter precipitation in the central Intermountain West states, and above average precipitation for the northwestern half of Wyoming. And the weather pattern that's expected to deliver these seasonal outlooks is one that presents more nickel and dime wimpy storms versus high impact major winter impacts. And so we'll be watching the evolution of that weather pattern to see if those small events continue to stack up without as much meaning, or if we can sneak in a few high impact atmospheric river events into the region. We'll wrap up with a summary of all those involved in the Intermountain West. If there are questions, they can be directed to the collection of climate centers and state offices around the region. And appreciate the time. Thank you very much.
Thank you so much, John. That was an awesome presentation. We appreciate that very much, albeit a little bit of a grim outlook for the Intermountain West. So next we will hear from Dan McAvoy from the Desert Research Institute. Dan, I will make you presenter. You should be able to share your screen.
All righty, let's see here. Are you seeing my screen yet?
Not yet. John, you might have to, there we go, now we see it.
Excellent. All right, well, thank you so much, Gretel, for having me here today to present this. And John, that was a great presentation on the current conditions and the outlook. I'm gonna focus primarily on snow and snow drought today in my presentation. I kind of want to start off with an overview of the concept of snow drought and kind of where it's at in kind of the research world. And then I'd like to talk to you all about the latest snow drought updates, which we have one coming out tomorrow, and give a kind of sneak peek of what the current snow conditions are looking like. And lastly, I wanted to talk about a research project we have related tangentially to snow drought, and it's more focused on snow temperature and water supply and runoff, which of course is all connected to drought in the long run. I wanted to start a bit with kind of the overview of the concept of snow drought, what it is, what it isn't. And really the idea that snow and below normal snowpack is connected to drought and water supply. This is not a new concept, and this has been known for a very long time, over a century. We have Dr. James Church here on the left, who developed the federal snow sampler, or the Mount Rose snow sampler, which is still used today. It's this tube here that the surveyors go out once a month to take measurements of snow depth and snow water equivalent. And this was initially used and connected through statistical relationships to predicting spring and summer water supply, and it's still used today. The photo on the right is from a 2023 survey on Mount Rose. And really the snow sampler, the snow survey technology remains unchanged, which is pretty remarkable. But the technology around snow data, how we depict and understand snow droughts, the drivers, the impacts, that is all changing and evolving over time. And so really, I think what opened kind of the doors, and what opened a lot of eyes in terms of learning more and trying to better understand this idea of specifically around snow drought was the 2015 water year. And so these two maps here show the April 1st snow water equivalent on the left. All the reds are below 50% of normal, and there's a lot that are well below that number. A lot are below 25%. And then on the right is the October through March total precipitation percent of normal. And you see there's hardly any of those reds, and there's actually some greens there indicating the 90 to 109% of normal precipitation. And so this idea that you can have a very low snowpack even when you have normal or above normal precipitation, and what we've been seeing from climate change projections indicating warming temperatures. And so this is where a lot of folks really started thinking about how to come up with different definitions and classify snow droughts. Adrian Harpold's paper in 2017 was one of the first to really look at these definitions of snow drought, classifying a warm versus a dry snow drought. A warm snow drought being one that has near or above normal precipitation and still below normal snowpack. And again, this 2015 event was really eye-opening. This map here is showing the October through March mean temperature percentiles for that year. Pretty much the entire West is red, and there's a very large area in California, Nevada, Oregon, Washington, into Utah, parts of Wyoming that had that record warmest water year. So that temperature was clearly a factor in contributing to that below normal snowpack, even though precipitation was not record low for most places. And so it definitely was that 2015 event that really got me interested in thinking about trying to better understand snow droughts and how to classify them. And pretty much since then, I've been involved in research in trying to learn more about defining snow drought, looking at the drivers, the timing, and also I think where there's still a lot of room is understanding the impacts of these snow droughts. Different types of impacts. And so this is a figure from a 2018 paper that I worked on with Ben Hatchett, where we basically took the ideas that the Harpold paper presented at these warm and dry classifications, where you basically look at just scatter plots of, on the x-axis here, it's percent of median precipitation, and then on the vertical axis is the snow courses showing the April 1 percent of median snow water equivalent. And this is for the northern Sierra Nevada region. And so we looked historically at these, the snow course data going back to the 1950s. And so you can see when you throw them on a scatter plot like this, they fall out into these bottom quadrants, which on the bottom right are the warm snow droughts. And on the bottom left are the dry snow droughts where precipitation is extremely low, as well as the snow water equivalent. And so one thing that came out of looking at this is that 2015 event is in those really dark brown dots there, falling into that dry snow drought quadrant. But we know temperature was in it, played a role there. And so there's this idea that snow droughts can be dry, but also warm. In this case, you see a lot of these dots are near zero for snow water equivalent, but the precipitation for October through March was anywhere from 50 to 70% of normal. So how can we work towards better understanding the dry and warm categorization of snow droughts? And then to further move this research forward, we kind of took that framework, just the 4 quadrants of different types of snow droughts, but really wanted to emphasize that instead of just looking at these snow droughts at a single point in time, like April 1st, there is a lot of reason to track these throughout the entire season. And so basically, we developed this snow drought phase diagram concept, where on the left is an example for the Central Sierra Snow Lab. And so each dot basically tracks that precipitation snow water equivalent phase space daily throughout the entire season. And so you can see how this area moves in and out of snow drought and can help understand kind of the drivers and some of the impacts that you're seeing. We've developed this diagram on the right that kind of helps explain this, because there are a lot going on in these diagrams. And one thing that we also started using was the US Drought Monitor percentile drought percentile classifications to define these kind of snow drought categories. You can apply this at a point scale like what is shown here, but there's also applications to this at basin scale to look at larger regional scale snow drought patterns and impacts. But there's still a lot of ongoing work on how to define snow droughts and understand them. This figure here is from a 2023 paper from Heldmeyer et al. Basically showing 3 different ways using different variables to classify snow droughts. On the left is the new method that they proposed in this paper that still uses cumulative precipitation, but instead of just using SWE, it actually uses the ratio between SWE and precipitation, which would indirectly account for that, which would indirectly account for the impact of temperature, where the SWE to P ratios change when you have warmer temperatures and more rain falling instead of snow. In the middle is the Harpold methodology that simply looked at accumulated precipitation versus the April 1 snow water equivalent anomaly. And then on the right is another method from Drought et al. In 2019 that again still used that accumulated precipitation. They used SWE, but then they also used a temperature metric called thawing degree days, which basically accumulates temperatures above freezing throughout the year to directly incorporate temperature. And you see that all 3 methods show different patterns in terms of which years are snow droughts and which ones are warm and which are warm and dry. And so the point being here is that this is still a very active area of research, and there's no singular way to define this. This kind of reminds me of what has been going on with flash droughts over the years, which are still an active area of research and used in operations now as well. But there's lots of different ways you can define them, and it depends on what your application is and what kind of questions you're asking. So with that, I wanted to move into discussing the NIDIS snow drought updates. And so these were first developed or first released in April of 2018. Again, as I mentioned, that those first papers on kind of defining snow droughts came out in 2017 and 2018, and there was actually quite a bit of media coverage around some of that research, and there was AMS released their definition of snow drought, and there was a growing interest in kind of being able to understand these throughout a season and have some way to communicate what's going on for a generalized but a drought-informed public can kind of understand this throughout the season, and that's where these snow drought updates came in. We wanted to bring awareness of the impacts, also the data and tools that are developing and being used, and these cover the Western U.S. That says CONUS, but it's just the Western United States right now. There has been talk about expanding this to other parts of the U.S., but for now it's the Western United States. Also Alaska we discussed, and so on the right here are just a couple screenshots from the snow drought update that was released in April 3rd of this year. And so it has kind of the drought early warning system regions. It mentions here that these are updated every 4 weeks from December through June. And we put some kind of key statistics in here, like the percent of the snow tell stations that are below median and also below the 30th percentile. We write a little summary here as well. But there is a process that has been developed over the years, and it's evolving, but we've kind of stuck with the same process for these updates over the past several years. So myself at DRI and a number of folks at NIDIS, some of the regional drought early warning system coordinators, as well as the communications team, work on drafting the initial text for these once a month and using putting in visualizations as well. We rely very heavily on the wonderful NRCS SNOWTEL data and the website and the graphics that they produce. We use a lot of those graphics in these snow drought updates. We also create some of our own graphics to throw in there as well. For example, on the upper right there, This is again from the April 3rd, 2024 update. This is just showing the SWE percentiles for that date, but just highlighting in colors, the same colors as the US Drought Monitor percentile thresholds there. So you can see kind of the areas that are most impacted by snow drought kind of in a quick snapshot visualization. So we write these drafts, but then we also solicit feedback from a group of regional experts who then have time, a short amount of time, but they are wonderful to work with, and they review what we've written. They provide their own regional, local feedback and things that we can add or change. And then we release these updates once every 4 weeks. Starting tomorrow, the first one will be released. And so again, we have these graphics. We also summarize key points. Just in the last year or two, we started breaking this down more regionally, where initially we kind of had one kind of large, a few paragraphs summarizing the text for the entire West. Now we summarize by regions, including the Sierra Nevada, the Cascades, the Rocky Mountains, Arizona, New Mexico. So we have these different regional breakdowns to allow to get into a little bit more detail about what's going on for you regionally or locally. And again, I really want to emphasize the partners here from our review team. This is just some of the groups that we work with. There are others that are not shown on here, but of course we work with we have reviewers from NRCS, several of the NOAA entities, including National Weather Service and the River Forecast Centers. We have a number of university partners. We have Oregon State University listed there. Several of the water resource departments throughout the Western US, including Idaho, California, Nevada will chime in sometimes, Oregon. And also a number of the state climatologists. So I have the American Association of State Climatologists there, but we do get feedback from a number of our state climatologists. So it really is a collaborative effort in putting out these things that get turned around in about a 3 or 4 day time period. And so this is a slide courtesy of NITIS, just kind of mentioning what they have available on the drought.gov website. And I realize now that maybe should have actually put these links in here. I do not know if the slides will be accessible so you can access the hyperlinks, but we can always share these afterwards with the direct links. But there's a direct link to the water year 2024 summary. There's also an archive of past updates. There is a link to research that's going on in the snow drought world, and then also to the kind of snow drought data and maps and tools page, which has the current snow drought status updates. That's where the one that's released tomorrow will be hosted. And so just a little snapshot of some of the things you might see tomorrow in the update that is released. We heard some of this from John, but hopefully you can dig in a little bit more. And so this is a similar map to what John showed, basically showing the percent of median snow water equivalent from the SNOTEL stations and the basin averages there in those large numbers. In terms of at the station level, the SNOTEL stations, 57% of the SNOTEL stations were below median SWE as of December 8th, and 31% of those sites were below the 30th percentile, so approaching those snow drought thresholds. But regionally, the worst conditions, unfortunately, were largely in that Intermountain West states of Wyoming and Arizona, and also parts of Montana, where you can see some of these basin level SWE values are below 60% of normal. John also mentioned this, but it is early in the season, and these SWE anomalies can change pretty rapidly, considering that the climatologies for this time of year are still fairly low, and so a big storm or two can quickly change things in terms of the percent of normal SWE there. And I did want to put a quick spotlight on the Snake Headwater Basin that spans western Wyoming into Idaho. On the left here, we have the trace of for that basin of the snow water equivalent for this year in black, last year in this gold orange color, and then green is the 1991 to 2020 median. And so starting off very well below normal for this time of year. And so as of the 9th, the SWE value was 2.9 inches, whereas the climatology value is 4.9 inches. So right around half of where we should be for this time of year for the basin. But again, things can change quickly. We saw last year that things started off pretty slowly and turned out not so bad by the peak SWE time and during the snowmelt season. But again, this is one of the regions that is already in severe and extreme drought based on the latest US drought monitor. So a place to continue to monitor for sure. And so the last thing I want to touch base on and shift gears a little bit here is a research project at the Desert Research Institute, also in collaboration with the NRCS that I'm working on. It's being led by Dr. Ann Hegley here at DRI with several other DRI folks and some NRCS folks. And it's being funded by the Bureau of Reclamation Snow Water Supply Forecasting a grant opportunity. And so, yeah, I want to give an overview and a quick update on this as it relates to a new method to measure snowpack temperature, which I'll explain how that relates to runoff and modeling, and in the end, snow drought and just water supply and drought conditions overall. And so these are some slides that I borrowed from Ann, so I'd like to thank her for these. And so why do we care about snowpack temperature? Well, we don't hear about it that much, but it's actually an extremely important variable related to the timing of snowmelt, and also very critical for flooding, flood forecasting, and water supply. And so basically, when you have the temperature of the snowpack reaches 0 degrees Celsius or 32 degrees Fahrenheit, it becomes what's called ripe, and that means it's ready and able to melt. And so the energy in the snowpack has warmed it up enough where it's able to melt. And so this is something that is a part of operational models that are used for flood forecasting, water supply forecasting, used by the National Weather Service, the river forecast centers. And those models incorporate the snowpack temperature and also the cold content of the snowpack. But the issue is that it's all model data. There's hardly any validation against observations, and we don't have a good sense of the spatial variability of snowpack temperature, and there needs to be more work in understanding and incorporating this into these models to hopefully improve predicting the snowmelt and water supply forecasting. So in terms of what has been tried in the past, there have been attempts going back to the 1940s to measure snowpack temperature continuously. So a lot of these are kind of fence-based methods where there's thermistors or thermocouples kind of going up these fences trying to measure snowpack continuously. And this has really, most of these methods have failed in terms of continuously measuring these variables. Snowpack, particularly in places like the Cascades or the Sierra Nevada, can be very heavy and dense and has kind of ripped apart some of these methods. And still, there's not a good way to get this information spatially and continuously through time. And so the idea that Dr. Hegley has developed was to use a non-contact infrared snow temperature profiler, an STP, and it's pictured there on the right, hanging off a cable. Basically an infrared temperature sensor like in your thermometers that you use to take temperature on the forehead. And it gets lowered down into the borehole left behind by the snow surveys. We go back to Dr. Church that I talked about in the first few slides. And so there are people going out every month throughout the winter taking these snow surveys, collecting snow water equivalent and snow depth and density, but snowpack temperature is missing. And so here's an opportunity for them to also collect snowpack temperature. And so with this new sensor that Dr. Hegley developed, basically this snow surveyor goes out, takes their SWE and depth measurement, then they can drop the sensor down the hole and get a temperature profile going up and down that column. And then with that, you can estimate the bulk cold content of the column of snow there, and hopefully compare this against some of the model output and help improve what those models are doing in relation to snowpack temperature. So in the first year, we're just starting the second year. This is a 3-year project. We did some of our own research grade observations in California, in the Sierra Nevada, in Colorado, and also in Montana, where we basically tested that STP sensor with the federal sampler there, as you can see in the picture here. And we also dug snow pits right next to that and used a temperature probe to then do comparisons of how the STP temperatures compared to the kind of gold standard of the snowpack temperature probes there. We did this several times throughout the year, and these graphics are basically just showing the comparison of the temperature probes, temperature on the horizontal axis and the snow depth, getting this these snow temperatures every 10 centimeters throughout the snow depth or throughout the snow column. And we found pretty good agreement between the STP, the new instrument, and the temperature probe. The areas where we did see the biggest discrepancies were in about that top 50 centimeters of snow that can really be highly impacted by things like solar radiation, mixing of the air down the hole that's left behind. And so we're working towards improving those readings in the top 50 centimeters. So we're now on to year 2 here, and this is an exciting year because now we're actually giving these sensors to snow surveyors that go out. We have a number of cooperators from agencies in California, Nevada, Colorado, and Montana. So hopefully we'll have these observations at 53 snow survey locations this year. We did a training with them last month to show them how to use the instrument. Boise State and the Airborne Snow Observatory have also jumped on board, so we're excited for that. And then really the goal is to start comparing these to the observations from the model outputs and then look further into the feasibility of how this could improve those models and operational integration into these models and just to the snow survey system. So ideally, we'd like to have these at snow surveys in states all across the Western United States if this turns out to be a successful project. So I will end there. And so thank you all for your time. And if there is time for questions or discussions, that would be awesome. So thank you.
Wow, thank you so much, Dan. That was an amazing presentation filled with lots of great new information about assessing snow and the evolution of doing so. We did get one comment about the technologies used for taking these snow measurements, wondering if the blue snow tube is not a technology that will last because there's some knowledge around it's too dark and heats up fast, changing how snow and ice may be measured and negatively impact the measurements. Do you have any comments or clarifications on that?
That's an interesting question, and I think that was referring to one of the pictures I showed that had a blue snow tube instead of a silver one.
Yes.
And I actually don't know the answer to that question, so I can't comment too much on that. If it was more general about the snow tube itself and the need for that measurement, I find it remarkable that measurement is still useful over 100 years later. And I think that there's still a lot of value in those measurements, even though we have things like the SnowTel stations that measure these daily or hourly. So I do think the snow survey in general will continue, but I can't comment much on the color of the tube.
Awesome. Well, thank you for that. And then, John, there is one question for clarification about a comment about the atmospheric river potential for the Intermountain West. I don't know if you want to revisit that with any clarifications.
Yeah, what was the question?
I guess the question was surrounding the potential or lack thereof of atmospheric river action heading south during a neutral La Niña, moving towards La Niña. I think it's a little bit forecast question.
So the ridge of high pressure that's expected to set up off of the west coast is a very classic La Nina type of pattern. It really shuts the door for a lot of major Pacific storm systems to push too far south into the western U.S. They stay more focused on the Pacific Northwest and the Northern Rockies area. And so when we look at the moisture sources, the air masses that are being drawn through the weather patterns, the atmospheric rivers are events that are tapping Central Pacific moisture. The low pressures develop offshore and then they move onshore and they draw this long line of high humidity from the Central Pacific. And then they ram that humidity into the mountain ranges of the western US and we get huge precipitation events. Usually record breaker, top, few percentile types of precipitation events. And the type of weather pattern that we are currently in and the extended range forecast ensembles are keeping us under will shut off a lot of that Central Pacific moisture from making it into the western US. Instead, our air masses tend to come more from the Aleutian Low or into the continental Canadian shield. And so those air masses are less humid and colder. And while they might present precipitation events, they don't provide those big impact, really significant snow accumulation events. And so just a different type of weather pattern that's tapping air from upstream in different areas. And those atmospheric rivers tend to be more associated with El Nino types of weather patterns when our jet stream is coming offshore or coming onshore from a little bit more of the Pacific Ocean, Central Pacific humidity air that draws in from those.
Awesome. Perfect answer. Thank you so much, John.
You're welcome.
Well, I don't see any other questions coming in. We can wait just a few more, a minute or so to see if anyone else wants to drop one in there. But I do want to take a moment here to thank both John and Dan for amazing presentations. I also want to let everyone know that you can register for the February 4th Intermountain West webinar. It is available on the NIDIS website. And please share broadly to your colleagues that may also be interested in these webinars. And not seeing any other questions coming in. Just a reminder, the first 2025 snow drought update will be available tomorrow and will be sent out to the listserv of all of the Western states that it covers. And we are so grateful for all of you for joining. Thank you.
Thank you, Gretel.
Thanks, Gretel. Thanks, Dan.
Thanks, Al. And happy holidays.